Today on Inevitable, our guest is Brent Minshew, co-founder, executive director, and chief scientist at Arête Glacier Initiative. And our topic is sea level rise. Arête Glacier Initiative launched earlier this spring as a nonprofit effort to fund and coordinate cutting-edge research that can improve sea level forecasts and explore potential glacial interventions. As Brent and I discuss, today's sea level models are fairly dire, with a significant amount of sea level rise already baked in by 2100, even if we as a society adhere to Paris climate targets, which we almost certainly will not. Today's models are also very wide, with estimates ranging from about a foot of rise up to 6 feet or more. Sea level rise is largely driven by the melting of glaciers and ice sheets, and the field of glaciology has historically had limited U.S. federal or university funding and coordination as compared to some of its earth science peer fields like atmospheric science and oceanography. Arête Glacier Initiative is hoping to overcome some of these challenges with its focused efforts. Brent and I discuss all of this, as well as some of the specific physical interventions that they're planning to explore. The conversation was a good reminder to me of why work around climate change is important. We can get caught up in talking about the decarbonization of this or that industry, or the impact of AI on the power grid, or whatever nuance you want. But at the end of the day, there are some incredibly large forces at play that have the potential to drive profound, almost incomprehensible change to the world around us. It's hard to fathom the size of a glacier, just as it's hard to imagine what multiple feet of sea level rise might mean. And I'm glad to know that Brent and his team are working to build awareness around the issues, better model outcomes, and identify possible solutions. From MCJ, I'm Cody Sims, and this is Inevitable. Climate change is inevitable. It's already here. But so are the solutions shaping our future. Join us every week to learn from experts and entrepreneurs about the transition of energy and industry. Brent, welcome to the show.
Thanks for having me.
Boy, I have heard about the work you guys are doing from a few folks that are very close to MCJ. Doug Daniels, who I think is engaged with you guys in some way now, and Mike Schreppert, who was a recent guest on the show and a friend of the firm. You guys are doing some pretty mind-blowing work. When I first heard of the idea of glacial interventions, I think it was probably in Kim Stanley Robinson's book, The Ministry for the Future. Stan has also been a recent guest on the show, and I think in the book, which is fiction, they were drilling down deep into glaciers to suck water out from the base of them and try to refreeze. And it was science fiction. And yet here you are trying to figure out ways to deal with this large problem. So that's the context I bring into the conversation. I'm excited to hear more about it from you.
Yeah, definitely. Thanks for having me. I'm happy to talk.
Why don't you start with just a definition of what is the work you're doing at Arête?
Arête Glacier Initiative, it's a new nonprofit that we formed. We just launched officially on March 21st. So the first International Day for Glaciers, as designated by the UN. And we really formed to kind of occupy this translational space between taking the knowledge that we develop in basic science research to understand how fast glaciers and ice sheets are evolving and translate that into both practical applications from a forecasting perspective to provide the knowledge and the actionable information that people need to be able to adapt to sea level rise. And also to think about taking those same questions that we need to answer to do better forecasts and flipping them around and asking questions about, is there anything that we can do within the glaciers to directly intervene to try to slow down rates of sea level rise? And so we at Arête are particularly focused on at least early stage development of ideas that really focus on trying to get glaciers to freeze themselves to the bed. This is something that happens as part of the natural process. So we know to an absolute certainty that under the right conditions, this sort of thing could work. And then the questions that we are seeking to address and through these early stage developments and so forth and research is whether or not we can recreate those conditions in places like Thwaites Glacier at the speed and scale that's necessary to be able to stabilize the ice sheet.
What is Thwaites Glacier?
So Thwaites Glacier, it shows up in the media sometimes as the Doomsday Glacier. It's dubbed by Rolling Stones, given that name a few years ago. Thwaites Glacier is really kind of the keystone to the broader West Antarctic ice sheet. And so the West Antarctic ice sheet is a special ice sheet in the world. It's what we refer to as a marine ice sheet, which just means that it's an ice sheet that's resting on the seafloor. The bed of West Antarctica is up to about 2 kilometers or so below sea level. And because ice floats in that configuration, you can have buoyancy-driven feedbacks that cause a rapid evacuation of ice to the ocean, so rapid rates of sea level rise. And so Thwaites is this Florida-sized glacier. It is really one of the most vulnerable points in the West Antarctic ice sheet because it's very wide, it's exposed to warm ocean water, and it's kind of a straight shot from basically what amounts to the edge of Thwaites right now to the heart of the West Antarctic ice sheet. Put succinctly, if we are going to get 2 meters of sea level rise by the end of this century, it has to come from Thwaites Glacier. And so this whole scenario, this potential for Thwaites leading to a broader collapse of the West Antarctic ice sheet is the largest source of uncertainty in our projections of sea level rise within the lifetimes of children who are alive today.
So Thwaites essentially, A, is a very large ice sheet itself. You said Florida-sized. But B is also essentially the wall of defense between the ocean and the rest of the West Antarctic ice sheet. Am I understanding that correctly?
That's right. So Thwaites is a special part of the West Antarctic ice sheet that's flowing particularly fast, and it is the most vulnerable part of the ice sheet.
I mean, it's called the Doomsday Glacier. We spend most of our explorations on this show understanding decarbonization and how we can, as a society, as a global economy, look to cut back on carbon emissions from our industrial process, from our energy systems, et cetera. You're coming at this problem from a different place, which is, hey, a lot of this is baked in. What can we do to stop what's already baked in, even if we do everything we can around decarbonization? So my question to you is, how baked in is all of this already?
It's still a little bit of an open question, but certainly the preponderance of the evidence at this point suggests that Thwaites in the broader West Antarctic ice sheet is in an unstable configuration. And what that means is that there are internally driven feedbacks, specifically the fact that ice floats, and there are buoyancy-driven feedbacks within the system that are going to continue no matter what we do with CO2 concentrations or emissions going forward. So certainly we need to act to decarbonize the economy and reduce emissions. This is eating a good diet and exercising as part of a healthy lifestyle. But this instability, which is likely at play in Thwaites Glacier, and therefore the rest of the West Antarctic ice sheet, is something that will continue no matter what. Which is to say that if we could snap our fingers and bring CO2 concentrations in the atmosphere down to pre-industrial levels tomorrow, we would still not be out of danger for the sea level rise question and the potential collapse of Thwaites Glacier.
This is a terrible analogy, but you have a large cocktail with a big ice cube in the glass. At some point, that ice cube has already started melting. It's sort of what I'm hearing from you.
That's right. The difference in that analogy, though, of course, is your ice cube in your cocktail is floating. Then as far as the level of your cocktail is concerned, it doesn't matter if it melts. Our concern with Thwaites is that you have your cocktail and you're happy with it, and we're concerned that we're going to dump more ice cubes into the cocktail and cause it to overflow. That is sea level rise. So sea level rise going forward, to a good approximation, is directly related to how fast the glaciers are flowing, how fast they're moving ice from the land to the ocean, which is the pouring of the ice cubes into the drink.
What do we expect right now, barring any interventions, we are likely looking at in, call it our lifetimes or the lifetimes of our children, maybe?
If we take, for example, the published values that we have in the IPCC, which is arguably our most authoritative source that people use for a lot of planning, the range of values is somewhere between about 1.5 feet and 6 feet of sea level rise by the end of the century. So within the lifetime of today's children. If we translate this in terms of human impact and impact on societies and communities around the world, we're looking at best case scenario about 2.5 million people displaced for every inch of sea level rise that comes up. So if you're looking at 1.5 feet, and we're looking at low end projections of something like 50 million to 100 million people losing their homes in the coming decades. And that's the best case scenario. That's if we meet Paris goals. That's if the West Antarctic ice sheet is not actually unstable. So the worst case scenarios, if we think about the potential for the collapse of Thwaites and kind of broader collapse of the West Antarctic ice sheet over relatively short timescales, we're looking at about 6 feet of sea level rise. And so that translates on the best case scenario, you're still talking about hundreds of millions of people losing their homes. It's really an exponential impact on societies. If you count in all the different factors, we're looking at closer to 1 billion people or so being displaced.
Just to make sure I'm following what you're sharing, Brent, I feel like when we talk about climate adaptation, so much of the focus is on, oh, there's extreme weather, there's terrible wildfires, there's an increased amount of hurricanes and wind and hail and floods. You're talking about something that is an order of magnitude, potentially greater impact here. And I heard you say that the baseline scenarios you were talking about don't even contemplate the dissolution of this Doomsday Glacier, this Thwaites Glacier. This is just what's already baked into the system now, that we're talking 1 to 1.5 feet of sea level rise, which is millions and millions of people displaced from their homes.
That's right. That's if we meet Paris goals and if the West Antarctic ice sheet is stable. Those are two big ifs. That is the best that we can hope for going forward under current scenarios and under a current understanding of the system.
Unrelated to, you said, if we meet Paris climate goals. So even if we decarbonize more aggressively than we have been, this is essentially the baked in outcome today.
That's exactly right. And to give you a sense of context, about 50 million people were displaced by World War II. And so the best case scenario that we're looking at is a displacement of people of order World War II. The worst case scenarios that we're looking at, if Thwaites goes, we're talking 10x, 20x World War II levels of displacements of people.
So your work today is on this latter, again, doomsday scenario, and we're going to spend most of our conversation talking about that. Why is there not more alarm bells just on the consensus baseline scenario today and more action about it? It feels like what you're sharing to me is more extreme than I have personally even contemplated, and I work in this space.
There's a couple of things that come into this. Number one, the field of glaciology, which is what makes these kinds of projections, is a relatively small field. Traditionally hasn't received a lot of attention. So funding-wise, we don't get a lot of attention from federal sources and so forth. Just to cite as an example, NASA's Cryospheric Sciences deploys about $2 million a year or so in funding. And so that keeps our field small. It's hard to really have a platform and to get the story out when you're a relatively small field and you're immersed in the current news cycle and the discussions at a societal level. Beyond that, I guess the second part of my answer is I honestly don't know. It is the kind of impact that has always been around. My career in this space has spanned about 15 years. And the story that I'm telling you today is the same story that we've had for about 15 years or so. Why it hasn't received more attention is beyond my expertise to comment on. But right now, especially with Arête, especially through outlets like this, we're seeing a lot of connection with this story. So as we tell people this story, as we point to the findings of the scientific field, as we point to things like the IPCC and hold it up and really point to these pieces, then I think that the story seems to be resonating quite a bit now. So I think it's gaining a lot more attention as we go forward. There's additional pieces that start to make this feel less abstract. I think that the sea level rise story for a long time has been a longer time horizon discussion, that these things could happen over multi-centennial timescales. As we learn more and we start to understand the potential for the rates of collapse of these particular systems, then we can start to tie it more and more to everyday timescales. For example, the global economy. And one of the bases of the global economy is the U.S. housing market. This is an important consideration. And so what we're seeing right now in kind of the U.S. housing market is this connection between kind of insurance and how insurance companies are responding to increased flood risks and so forth, of which sea level rise is by far the largest uncertainty in future flood risks. We're seeing insurance companies start to respond to that. We're seeing insurance companies pull out of coastal states for a variety of reasons because these things are getting more and more expensive. And we see this condition where kind of our forecasts of sea level rise are starting to have real economic impacts in terms of availability of insurance and thus the value of the coastal housing market. And so the threat of sea level rise in these doomsday scenarios is very real over the lifetime of our children. There's also a concern today, right now, and thinking about the value of coastal real estate, whether you live in a coastal area or whether or not you live in the broader global economy, these sort of changes in availability of insurance and thus the potential for people to be able to get a mortgage to buy homes is very real. It's here today. So the threat is really present, and it certainly plays out over kind of mortgage timescales. And I think that that's a story that hasn't quite had a lot of air to breathe and kind of to get out into the broader world. The last thing I'll point out is, if you don't mind me musing about a kind of a historical aspect of the science. So the field of glaciology has also undergone a recent evolution in its understanding of the changes in responses of ice sheets. So one of the early IPCC reports from, I believe it's 1995, plus or minus a year, says that ice sheets are stable over timescales less than about 10,000 years. And so the concern about sea level rise was really related to mountain glaciers and so forth around the world. If you take all of the ice in mountain glaciers around the world and you melt it, you don't really see a significant change in sea level rise. From the early days of thinking about IPCC, it was sort of a minimal problem, that the concern about melting glaciers was more about freshwater resources than thinking about sea level rise. And then there was an event, a natural experiment that happened in the early 2000s, 2002, 2003. There was a collapse of this area of Antarctica called the Larsen B ice shelf. An ice shelf is the floating extension of the ice sheet. So this area, the Larsen B ice shelf, which is roughly the size of Rhode Island, shattered in a period of just a few weeks. So this was a large area of an ice shelf the size of Rhode Island that was a couple hundred meters thick, that had been there for tens of thousands of years, since the last glacial maximum at least. And then it was gone in a matter of weeks, which was sort of beyond our understanding of things. And then we watched the glaciers that were feeding this ice sheet speed up. And that showed that the assumptions behind the statement of ice sheets being stable over about a 10,000 year time scale was incorrect. And so it was this profound shift in our understanding of how quickly ice sheets can respond. And so now we understand ice sheets to be highly dynamic systems that are capable of raising sea levels quite rapidly.
For listeners who want to understand more about that particular event, we had an episode a couple years ago now with a polar explorer named Will Steger, who was the fourth person ever in the history of the world to have reached both of Earth's poles. And he talks about his experience of visiting Antarctica both before and after that event. And it's a pretty mind-blowing and compelling story to hear. Thank you for expounding on all of that. It really strikes me, and I know I want to spend most of this time talking about your work, which is trying to prevent the worst case scenario, even worse than everything you just laid out. But it strikes me that I think most listeners probably are not contemplating a world with a foot or so of sea level rise by the end of this century, and what that might mean to so many people and so much life as we know it around the world. I think where I want to go next with this conversation is baked into the name you've chosen for your organization of Arête. Maybe describe what Arête means and why you chose it as the namesake.
So it's a fun name because it kind of has three meanings to it, which are all relevant to our work. So an arête, as we spell it and as we pronounce it, is a thin fin of rock that separates two valleys that once held glaciers. And so they're a rock formation that influences and is influenced by the flow of glaciers. And then symbolically, it separates two glaciers that kind of represent two possible futures, one where we do something and one where we choose to do nothing and we continue in our process. If we tweak the spelling of Arête a little bit, if we add an R to it, that is the French word for stopped. And so, this is thinking about being able to slow down rates of sea level rise and have an impact around the world. And then if we keep the single R, but we lose the hat over the E, that is an ancient Greek philosophy called arete, which is about the pursuit of excellence and the fulfillment of a higher purpose. And so there's kind of have this nice threefold meaning to the term. I quite like the visual of the rock formation and then all of the deeper philosophical aspects that can come with it.
Thanks for bringing a little bit of poetry to what has been a little bit of a bleak conversation thus far. Diving into the actual work that you're doing, as I understand it, you've recently raised funding yourself, which you are then turning around and turning into an RFP process where you will thus dole out grants to additional work in your space. Maybe describe what your role is in the ecosystem, the work that you're directly facilitating, and then where you're hoping to see folks pick up the mantle from the leadership position that you're staking out.
The purpose of Arête right now is that acts as a vehicle for philanthropic funding that comes into the field. So we have raised a little bit more than $5 million now, and that's all effectively new money that is rolling into the field. This is from philanthropists who have not previously contributed or funded efforts in glaciology. So we're very happy about that. The field needs funding, and we need to understand what's going on. And then Arête also fulfills both as a funder and as a coordinating hub to be able to fund researchers and coordinate efforts to really drive toward a near future where we can do a much better job of forecasting sea level rise. If you remember the range that I mentioned before, 1.5 feet to 6 feet, that's untenable from a planning perspective. And we need to be able to ideally narrow that range, but at the very least, be able to quantify the likelihood of any of those outcomes. That's not something that we as a scientific field are capable of doing right now. We can't really say with any confidence which one of those scenarios is more likely to happen. And so in the near term, we can concentrate research efforts. We can bring in software engineers and people with relevant skills to build better forecast models that are able to take advantage of the observations that we have so that we can produce forecasts with ideally a narrow range, but at least quantified uncertainties. And we can start to get at this basic question of how likely is this doomsday scenario? How likely is it that Thwaites and the rest of the West Antarctic ice sheet ends up collapsing over human timescales? What we know about Thwaites Glacier right now is that its collapse is almost certainly inevitable. So it's not an if it collapses, it's a question of when. But there's a large range of uncertainties in that, so we want to be able to direct efforts in that.
Centuries or millennium of uncertainty, or within decades of uncertainty?
Multiple centuries of uncertainty. So collapse is entirely possible within this century, within the lifetime of today's children, but maybe it could also take 500 years. And we really need to know what is the probability for any given time span. We're pretty confident that if we go out 1,000 years, it's probably largely gone, that there are large sections of the ice sheet. But will that happen in the next 50 years is very much an open question. And so we need to be able to address that. And we need better models. We need better observations. We need a dedicated monitoring campaign in West Antarctica that allows us to really understand what's going on so that we can ideally be able to constrain precursory signals and so forth and be able to provide early warning forecasts for what's happening in the ice sheet. And then beyond that, with Arête, also organizing and helping to fund early TRL efforts. So TRL, NASA's technology readiness levels, things that we typically do for developing complex technologies, like sending people to the moon, stuff like that. We need to be able to fund a lot of early TRL work in understanding what are really our options for intervening. We need to be able to move past where we're at right now, which is kind of the theoretical stage, the early TRL levels, where we're filling these things out in models and start to develop more and more precise plans for how interventions might work. What are the risks? What are the scales? What are the costs? And so forth.
So part of the work to both understand the scope of the problem, but get better at the models of what may happen or what is likely to happen, and be able to be better at predicting the future. And part of Arête is actually funding early, hard, deep tech work on what some interventions could possibly be. Am I following correctly?
That's exactly right. So we know that we have a problem and we need to develop solutions, but we also need to do a better job of defining what exactly the problem is. How fast do we need to move, at what scales, and so forth. And so Arête is dedicated to answering both of those questions.
And you had earlier cited the amount of funding that goes into something like NASA's glaciology understanding. Give us some order of magnitude of, you said you've raised a little over $5 million. How sizable is that in your field? Is this going to enable a great leap forward of understanding in this space? Or are you just also starting to scratch the surface and need to ultimately be an order of magnitude larger to make the type of impact you have in mind?
$5 million is a considerable increase in the amount of funding that is available to the field. I'll give you an example. There was a recent effort known as the International Thwaites Glacier Collaboration, which is a collaboration between NSF in the US and NERC, which is the NSF equivalent in the UK. And that funded about $5 million a year in research. And that was a big boost to the glaciological community in terms of funding. And so we are of order that, and we look to ramp up our level of funding. The International Thwaites Glacier Collaboration, I should mention, was only for 5 years. That has now ended, and so that funding source has dropped off. We will need much more funding in the future to be able to really understand and answer these questions. But given our initial conditions of funding right now, $5 million is a big step forward.
Hey everyone, I'm Yin, a partner at MCJ, here to take a quick minute to tell you about the MCJ Collective membership. Globally, startups are rewriting industries to be cleaner, more profitable, and more secure. And at MCJ, we recognize that a rapidly changing business landscape requires a workforce that can adapt. MCJ Collective is a vetted member network for tech and industry leaders who are building, working for, or advising on solutions that can address the transition of energy and industry. MCJ Collective connects members with one another, with MCJ's portfolio, and our broader network. We do this through a powerful member hub, timely introductions, curated events, and a unique talent matchmaking system and opportunities to learn from peers and podcast guests. We started in 2019 and have grown to thousands of members globally. If you want to learn more, head over to mcj.vc and click the membership tab at the top. Thanks, and enjoy the rest of the show.
Forgive my geopolitical ignorance, but Antarctica does not have a governing body in any way. So you're also in this strange world where the outcome of your work is going to affect any country that has ocean around it, and presumably many more countries than that, because it will dramatically create migration and impact global trade and et cetera, et cetera. And yet the subject of your work is not itself capable of requesting sponsorship in any way.
So Antarctica is very interesting from a policy perspective because it's much more like the moon than it is like anywhere else on Earth. It has never been governed by any single state. No child has ever been raised there. For most of human history, it's been largely inaccessible. And it's governed by the Antarctic Treaty System, which is something that came together during the Cold War. And so a lot of Antarctic science and exploration looks a little bit like space race and space exploration and so forth. How the Antarctic Treaty System ends up evolving over time to kind of recognize the threat to coastal countries around the world is an open question and is not my area of expertise. I will just say that the Antarctic Treaty System involves multiple countries who are signatories. So these countries are generally countries with extensive coastlines. They tend to be the wealthy countries around the world. The presence in Antarctica, the amount of funding and so forth that's spent in Antarctica tends to be one of the determining factors, as I understand it, in terms of the country's influence in the Antarctic Treaty System. So the United States is one of the bigger players in the Antarctic Treaty System due to the amount of funding and logistics that are maintained by the U.S. within Antarctica. And then there are changes afoot with anything related to the polar regions and so forth. The politics appear to be changing, in large part because China, for example, is really ramping up its presence in Antarctica and the amount of funding that it's spending, and other countries around the world as well. South Korea is really stepping up and providing a lot of resources and funding for ice cutters and so forth. So there are more countries that are starting to come in and starting to do science within Antarctica, and so therefore starting to have a presence there and starting to spend money. Similarly, kind of mirrors the moon a little bit in that the access to Antarctica is starting to open up to more than just the traditional players.
Let me pull on that moon metaphor a little bit. So what we've seen in terms of space exploration is a shift from government-funded work to private-funded work with the rise of SpaceX and the like. In climate as well, we have seen big tech companies and whatnot starting to spend significant amounts of money, both on their own net zero commitments, but also in being early customers of things like carbon removal. And Microsoft, for example, is the 800-pound gorilla in carbon removal globally today. I'm curious, you mentioned the first half of your mandate is around modeling and better data understanding and predicting likely scenarios. That's the purview of AI and ML. Are you starting to see big tech lean into your world, recognizing that if the global economy is going to be as impacted as you are saying, you and not just you, but the IPCC report is saying it will be by the end of this century, presumably every major corporation on the planet has an interest in trying to help this problem?
That's definitely right. We're starting to see quite a lot of interest from particularly individuals. So you mentioned Mike Schroeper earlier, who's one of our founding funders through the Outlier projects, but also people who are coming in with a lot of tech experience who are looking to help out on the technical side of all of this. We have folks that have a lot of experience in industry who are now helping us build out database tools and things like this to deal with the trove of data that we have coming in from satellite observations, We're in early stage discussions with people who have a lot of experience in AI and ML models for physical systems that are starting to get interested in coming in and helping out with this problem. I mean, it's a fascinating physical system to help out with. And if you're excited about physics and you're excited about like AI and ML enabled models and all these kinds of things, like, it's a perfect opportunity.
I guess I answered my own question with the way I introduced our conversation. Mike Shepard, who was the former CTO at Meta, is involved, and Doug Daniels, who is a very senior engineering leader at Datadog, is involved. And so you're able to pull on these types of big minds and hopefully their resources, and eventually, hopefully their organizations also stepping in to support the work that you're doing.
Arête was only formed a little over a year ago, and we've already garnered a lot of attention. It's a big problem. We talked about the doomsday scenarios earlier, but I want to make sure that we don't miss the fact that it's a really exciting problem. If you're the type of person that is really excited about solving problems, if you're excited about physical systems, if you're excited about the possibility of solutions and so forth to all these changes, it's a perfect area to really start to work in. And particularly thinking about the interventions, if you're looking for something that is really high leverage, there are potential solutions that are really high leverage within these systems. So relatively small containable scales having a big global impact, then it's a perfect problem to get excited about as well.
Let's dive into a few of those. We've talked about the need for modeling and understanding. Let's dive into what are some of the ideas that could actually halt the flow of ice sheet collapse and glacier decline.
All of the ideas that we're very excited about are motivated by natural phenomenon. So the important one to kind of point to is to say that glaciers in Antarctica freeze themselves to the bed naturally as part of the natural cycle. And when they're frozen to their bed, they're effectively stable.
My basic understanding of glaciology, glaciers naturally have liquid underneath them and are naturally moving. That is the natural state of things?
That's right. To a really good approximation, Antarctica is both the world's largest desert and the world's largest wetland. And so the world's largest wetland on the bottom side of the ice sheet. So there are active river, lake, and stream networks and so forth underneath the glacier. And lots of fresh water flows out from underneath the glaciers all the time. And that water, in the right configuration, acts as a lubricant to the flow. So as we mentioned before, to a good approximation, rates of sea level rise are rates of glacier flow, how fast the glaciers are flowing. And the glaciers that we really care about, like Thwaites and the ones that can contribute the most to sea level rise, are flowing fast largely because they're sliding along their beds. So their beds are muddy or their beds are rocky. There's a lot of water lubricating these beds and allowing for this fast glacier flow. And so we know from observations that under certain conditions, glaciers will get themselves into this process where they start to freeze themselves to the bed. And the way this works is simply that the majority of the heat provided to glaciers that are flowing relatively fast is due to frictional heating. Kind of like if you just stick your hands together and you rub them together, everything starts to warm up. That's one of the main sources of melt of ice and thus the supply of lubricating meltwater. There are natural feedbacks within this process that cause glaciers to get into the state where they tend to freeze themselves on more, or they tend to melt a little bit more and speed up depending on the different conditions. And so there's a famous outlet glacier in Antarctica known as the Kamai Stream that stagnated about 200 years ago. 250 years ago, it was flowing along relatively happy, somewhere around, I'm going to do this again with metric units, 350 meters per year, multiply that by 3, a little over 1,000 feet per year, somewhere around in there, which is relatively quick for a glacier flow. And then within a few decades, it shut down. It's almost not flowing at all anymore. The speeds are almost immeasurable. Our current understanding suggests that it did that between this feedback, between the lubrication and this frictional heating that's due to the cycle. And what's really interesting about that glacier is that most of the bed, as we gather from observations, appears to be thawed still. There's still water running in underneath it. There's still all these different pieces, but the whole glacier, and this is a sizable glacier, shut down because a few kind of isolated patches froze themselves to the bed. So this is something that really motivates our thinking about how interventions might work. So now if we translate this to a place like Thwaites, which is probably about 3 times or so the size of Kamai Stream, so order of magnitude, kind of roughly similar sizes, how would we think about getting Thwaites to freeze itself to the bed and thus stabilize it? Because all of these ideas, these doomsday scenarios that I talked about before, they're all predicated on the fact that the glacier is thawed and it's sliding along this mud that makes up its bed. One of the things that we know from observations of a place like Cam is that we only need to get the glacier to freeze relatively isolated patches. Back of the envelope calculations, which will be shored up in future research and so forth suggests that we're talking about maybe like 10 kilometer by 10 kilometer square areas, so roughly 100 square kilometers that you could work in and try to get the glacier to freeze itself to the bed. And the second thing from Cam, I keep mentioning freeze itself to the bed. This is a very important point in terms of the leverage points. We don't need to freeze the glacier to the bed directly. All we need to do is nudge the glacier into a state where it freezes itself to the bed. Again, because of this feedback between frictional heating, rubbing our hands together, and the development of the lubricating meltwater underneath. You create the situation where we have a real potential to intervene in a relatively non-intrusive way and in a way that mimics natural processes and in quite an isolated area. So we get very local interventions for this global benefit in terms of reductions in sea level rise.
Describe a few of them. I've seen on your website, you have a graphic that has 2 or 3 different interventions that could happen all laid out together. What are 2 or 3 of the most promising ones today that you think are worthy of funding with a grant from Arête, for example?
So within my research group at MIT, we're working on these things called thermo-siphons. Effectively, we're pumping heat out. All a thermo-siphon is a passive heat pump. It works just like the heat pump in your house, or if you don't have a heat pump, you probably have an air conditioner. Air conditioner is just a heat pump run in reverse. But they work the same way as that. But the neat thing about them is that in Antarctica, because the surface is very cold relative to the bed is thawed. The surface's average annual temperature is about minus 20, minus 30 degrees C in the areas that we would work. The temperature differential is enough to drive the heat pump itself. And so we can put these things in and we can pump heat, we can cool the bed effectively without any additional energy input once we've installed these things. And basically, it's as simple of a thing as you can imagine. It works a lot like the heat pipes that are in computers and so forth, deal with thermal bits. You sink a pipe that's sealed, you drill a hole to the bed of the glacier, you put this pipe in near to the bed of the glacier. The pipe is sealed, it has about 100 pounds of CO2 in it. And then 100 pounds of CO2 is going to be pressurized to about 400 PSI, 4x bike tire pressures, the kind of thing that an air compressor at Home Depot can deal with. So these are not exotic pressures by any means. But under these pressures, we expect that the CO2 will be a liquid at the bottom of the pipe. And so it'll absorb heat from the warm bed that will vaporize the CO2, which will rise through buoyancy toward the top. And when it gets to the colder pipe that's exposed to the atmosphere, the colder ice above, it will recondense. That releases the heat, the latent heat that it absorbed to evaporate. And then the CO2 will rain back down to the bottom of the pipe. And this whole cycle kind of repeats itself.
How deep of a hole? How deep of a pipe?
Yeah, so we're looking at 1,000 to 1,500 meters, being the thickness of the ice, somewhere around in there. So that's long relative to a lot of heat pumps that have been installed around the Arctic, for example. This is a very common technology used in the Arctic to stabilize foundations and whatnot. Those thermosiphons tend to be a little bit shorter, but there are a lot of thermosiphons that are being developed now for geothermal applications. So thinking about geothermal energy, there are prototype thermosiphons that have been developed and tested that are up to 3 kilometers long. So quite a bit longer than what we need. There's a little bit of development work to be done, but we're really kind of in this space that is between existing technologies and technologies that have been proven. So it's all entirely doable from a technical perspective.
And how do you replicate these environments in order to do testing?
One of the first grants that came out of Arête was building up laboratory capabilities to start to do this kind of thing. In particular, we're very interested in building, call them artificial glaciers in the laboratory. The technical term for these devices is a ring shear device. It's used very commonly in like civil engineering applications and so forth to understand foundations of buildings and other substrates for all these different conditions. Right now, there's one of these in the world. We've issued a grant to build the second one of these artificial glaciers that has the ability to provide tighter controls on temperature and water pressure and things like this so we can start to be able to test intervention ideas within the laboratory. And then we have plans to scale these out to larger and larger scales. So the one that we've issued a grant to start to build at the University of Wisconsin that fits in a room. And then there are plans to build out these artificial glaciers all the way up to roughly the size of a house and to be able to deal in these scales. And so what that laboratory infrastructure allows us to do is to move through, call it the mid-scale TRLs. So we move through a lot of laboratory testing. If we think about this as if we were building an aircraft, this would be our wind tunnels that we test out different ideas in. So it gives us the ability to rapidly and cheaply prototype and test different ideas in the environment. And then that gets us set up to start thinking about small-scale field trials and so forth in the later years as you move forward. These are all just examples. If we're thinking about things like thermo-siphons, for example, we can do a lot of kind of go, no-go testing within models because we're talking about putting a pipe into a viscous fluid, which is something that we have the technical capability to model because people build buildings all the time. It's similar types of aspects. So we are working on these conditions, asking questions like, can the pipe actually withstand the stresses that it will be exposed to in the actual environment? That's something we can definitely test in models quite well and then prepare for laboratory tests and further development. We will be able to answer questions within models of what is the appropriate scale of this thing. So I mentioned if we wanted to intervene, you're talking about 100 square kilometers, but there are obvious questions like where would you do this? What would be the grid spacing of these different thermo-siphons? That is, how many holes would you need to drill and so forth? These are all things that we're working on testing and developing within modeling frameworks.
This sounds like the world of digital twinning, where you can spin up a digital version of the Thwaites Glacier and essentially see what happens.
That's literally what sea level forecasts are right now at the moment. The projections that we get in IPCC, they are essentially a digital twin of the ice sheet. And so we can take these models, for example, and we can start to poke around. We can, for example, by fiat, just decide, like, if I increase the friction of the glacier in these areas, what is the response and over what time scale? So that's one set of testing. We can test in other models more precisely in detail, like what would a single thermosiphon pipe experience in terms of stresses as these things change. And we can start to build up this knowledge and infrastructure as we work forward.
What are some other interventions you're looking at?
Some of the other interventions, thinking about basal interventions, you mentioned Kim Stanley Robinson's book earlier, The Ministry for the Future. So that discusses an intervention that is related to drilling to the bed and pumping out this water that we refer to as the lubricating meltwater. So the character in Ministry for the Future, his name is Slavik, that does this. That's a real-life glaciologist by the name of Slavik Tulacek. So a colleague of ours that has talked about this idea since 2008, I think, or a little bit earlier, and thinking about how this works. Again, this leverages our understanding of the lubricating effects of water. And so we're interested and we're working on, actually soon to submit a manuscript that does some early stage testing, again, within models that ask questions about how much energy would it really take to do this? How effective would this pumping be? How fast do you need to pump? How many pumps would you need to install? And so forth. So it's a very exciting possibility as well. I would imagine that an intervention in the future, combines some of these two things, and that kind of gets us started.
What do you do with all the water you pump out? You can't put it in the ocean, obviously.
No, the ocean's too far away. So you spray it as snow over the surface. The idea is that water is far more potent as a lubricant in liquid form at the bed than it is as a weight in solid form, in snow form at the surface. And so there are technical challenges with all of these things, of course, that I'm happy to dig into and that we're quite aware of. But these are things that we can deal with in early TRL at a research level to gauge the viability. And then the third category of interventions that we mentioned on our website is effectively the combination of the two. We have it in an illustration in our cartoon as though it's a speed bump at the surface, which is a good representation of the effect that we're going for, but we wouldn't literally drill to the bed of the glacier and build a concrete bump. It just wouldn't be logistically feasible given everything that we know. But what we can do is we can, again, look at the natural system for our motivation. And we can say that in places like Cam Ice Stream and some of these other areas, if you drill down to the bed, in some cases, you reach this concrete layer of frozen dirt that's at the bed. In other words, what glaciers do naturally under the right conditions is they will dig themselves down into the bed because they're really heavy and ice is a viscous fluid that flows like honey. There are conditions, and this is very early stage work in theory, where we could manipulate the temperatures and the water pressures at the bed of the glacier to get the glacier to dig itself into the bed, much like a ship running aground, and start to, again, work out these processes. And so all of these are built around this idea that if we can put the brakes on, then what that means is really increase the drag and the friction at the base of the ice. If we can really mash the brakes, then we can slow down the glaciers. And one of the things, again, that we understand from the natural system is that once glaciers have frozen themselves to the bed, they will stay frozen for centuries. And so that gives us this ability without any additional input and maintenance on our part. So that gives us the potential to be able to intervene in the ice sheet in a way that slows down rates of sea level rise and gives decarbonization and these other efforts time to really take hold so that they can ideally move our climate back to a habitable state and to allow the ice sheets to slowly evolve over time as they naturally would.
If you had a crystal ball and could predict in the future, hey, we have done all the modeling we needed to do. We know what the impacts of this glacier are going to be. We have taken one of our interventions and gotten it to a TRL 9 and it's ready to go. How does something like that at the scale required get funded? What does the actual implementation look like 20 years from now if we're at the point where we're ready to actually deploy something?
Almost certainly some combination of large-scale government investments of order kind of larger public works projects and probably some private investment that comes along with it. When you think about what these investments are and you start to imagine the scale of these interventions and what it would take to do the logistics and the cost involved and so forth, it's significant, but it's of order the kind of thing that we do right now within societies. Back of the envelope calculations for what an intervention to stabilize the Thwaites Glacier might cost. And we compare that to the cost of building seawalls or other infrastructure around the coast, because we're going to have to do one or the other or some combination of the two.
Sounds like we're going to have to do the seawalls regardless.
Yeah. But of course, the higher sea level rise, the taller your seawalls need to be, the more coastline you need to protect and so forth. So if we compare it with kind of modern day cost of seawalls, you're talking a large scale intervention to stabilize Thwaites would cost a couple of 100 miles of seawall or somewhere around in there. A relatively insignificant cost compared to the cost of just dealing with sea level rise around the coastline. We can do calculations and we can show the complementary aspect of glacier interventions to reduction of CO2 emissions. So if we think about like the energy that it would cost and therefore the CO2 emissions that would be required in order to intervene in the ice sheet, and we compare that to the CO2 emissions from pouring concrete for all of these many, many thousands of miles of seawall and developing infrastructure and so forth, it's orders of magnitude less CO2 emission to do the glacier interventions than it would cost to fortify coastlines around the world. So the scaling is actually kind of neat. The cost of CO2 emissions to drill a hole to the bed of Thwaites Glacier, just taking into account the energy required to melt the ice all the way to the bed, you basically get one hole to the bed of Thwaites Glacier for roughly every meter of seawall that you could build. So if we needed 10,000 holes drill to start to stabilize Thwaites Glacier, that would be equivalent to 10 kilometers. So that would be like 6 miles of seawall, something like that. And that's just taking into account the CO2 emissions from pouring concrete itself. That says nothing about the construction costs or anything like that, the damage to coastal ecosystems and whatnot. There's huge leverage here from both a financial and a CO2 emissions perspective if these glacier interventions can really work out. Again, we're at early TRL levels, so we can promise nothing, but we know that the natural system does this. And so we know to a certainty that these interventions can work under the right conditions. And the question is, can we recreate those conditions in the places that matter at the speed and scale that we need to?
Brent, where do you need help?
Certainly fundraising is obviously a big part of this. We are open to philanthropic donations and so forth. For the bigger picture, in terms of listeners and how they can get involved, is similar to this question that you asked before. What are your skill sets? We need technical skill sets. We need people who understand how to work with large data sets, which is something that we're just now starting to get as a field. So how do you deal with big data sets? How do you develop ML and AI-enabled models that can efficiently assimilate these data sets and still accurately represent the physics of the system? We need people who are excited about policy, people on the ground and partners with organizations that talk to vulnerable communities around the world. We need to connect with industries, the insurance industry, mortgage industries, finance industries, and so forth. And we are starting to have these conversations, but we're just getting started. We're in our early stages. And so the more interest from people in terms of either direct funding or indirect through connections with members of Congress and so forth to get federal funding, international partnerships, and then technical expertise or just relevant expertise on all these different fronts.
I hope our listeners here are hearing this and thinking about ways that they or their organizations can come in and participate, because it strikes me that the work you're doing is under the radar from a relative impact and importance perspective.
Yeah, I think that's right. But it's great. Thanks for having me on again. It's really important to be able to talk to a broader audience about these problems and get more and more people engaged and excited about it.
Brent, thanks for joining us. You've really opened my eyes and hopefully inspired many here to think about ways they can contribute to.
Thanks for having me, Cody. It's been great.
Inevitable is an MCJ podcast. At MCJ, we back founders driving the transition of energy and industry
and solving the inevitable impacts of climate change. If you'd like to learn more about MCJ, visit us at mcj.vc and subscribe to our weekly newsletter at newsletter.mcj.vc. Thanks, and see you next episode.